So this is our third video for section 2.3, characterizations of invertible matrices. We're going to do a couple problems. These problems are going to seem kind of anticlimactic because they're fairly straightforward now that we have our theorem. One way to think of what Theorem 8 is all about is it gives us some shortcuts for determining if matrices are invertible. We don't have to use the shortcuts. We will always have our technique from section 2.2 that we can apply to find an inverse step by step. But it is going to be important for us to see how there are these shortcuts. There is these other ways of looking at invertibility. So let's go ahead and do these problems. And so I have a 2 by 2 matrix here. I want to determine if it's invertible. And what I want to do is I'm just going to observe here now. This isn't always going to be true, but notice that if I look at the columns separately here, 15, -6, that's a scalar multiple of 3 times 5, -2. In the other column, -10, 4. I can think of that as -2 times 5, -2. I'm trying to get the same vector here, so that's why I'm saying multiplication by -2. Now, let me see if I can make this work here. So if I could say 15 -6 is 3 over -2 times the vector -10, 4. Is that going to work out? I divide by 2, I get 5 times 3 is 15. 4 divided by 2, -2 times 3 is -6. What that is telling me is that one of the columns of my matrix here is a scalar multiple of the other. So the columns of our matrix are linearly dependent, right? That was one of our shortcuts to recognizing linear dependence. From Theorem 8, for a matrix to be invertible, the columns of the matrix must be linearly independent. Since the columns are dependent, so we can say, therefore, by Theorem 8, part, what do we call that? Part E, the matrix is not invertible. Okay. And I think sometimes it's not that hard to see that dependence of columns. If it doesn't take that long, right away you know there is no inverse for the matrix. Let's look at the second example here, 4 by 4 matrix. This only applies to square matrices now, right? And there are a lot of 0 entries here. I can see without too much trouble that this matrix is going to have 4 pivot positions. And if you need to go through a few row operations to convince yourself, that would be fine. So this matrix, this 4 by 4 matrix, has 4 pivot positions. Well, back to our theorem. Part C says that if we have n pivot positions in an n by n matrix, it's invertible. The inverse exists. So we can say, therefore, by theorem 8, part C, this matrix is invertible. We didn't find the inverse. The instructions just asked us to determine if the matrix was invertible or not. So we're done. And that's the end of the video lectures on section 2.3.